Thank you very much, Mona, and good morning, ladies and gentlemen. So the title of my talk today is Enhancing Machine Intelligence in Minerals Exploration with Human Knowledge. And the reason I've combined the concept of machine learning and human knowledge in the same sentence is that machine learning is very much a flavor of the month at the moment, or flavor of the year, or flavor of the decade, I'm not sure. But for machine learning to really work, it needs thousands or hundreds of thousands or millions of training data sets for it to be effective. And Google has those things from people's responses on the internet, or from millions of pictures of a cat or a dog, and to distinguish those things. We don't have those in mineral deposits, but what we do have is over 100 years of human knowledge, well documented in publications like Economic Geology, coming out of the MDRU, out of codes in Australia. So a really intelligent option would be to try and express that on a computer, and then get the computer to reason with that knowledge against the very large data sets that we have that are indeed too complex to be thoroughly interpreted by human beings. So that's what the graphic on the front page here is meant to represent. So in short, Minerva Intelligence is a private company focused on bringing the benefits of artificial intelligence technology to the mining industry. I've explained what that's all about. Surely we must believe that behind the morass of data we have, there must be a deep structure. And if we can find that deep structure and reason with it, we should be more effective than we are with our ad hoc databases. So we're focused on knowledge engineering to enhance human and organizational performance. We use AI technologies to do that, such as machine learning, and we include machine learning when appropriate. In my view, a good example of where machine learning would be appropriate, and which we're actively researching with assistance from people at UBC, is the extraction of features from magnetic surveys, and from gravity surveys, and from IP surveys, and so on. We can't reason about individual pixels in the results of the inversions of those surveys, or on the color ramps on a nicely colored up mag map. In order to reason about those, we have to have features extracted from them, like an inferred fault, or a polygon which may indicate a deep intrusion. Once you've got something like that, you can start reasoning with it. The signals processing engineers who've been working on things like that for years in the Department of Defense in the United States call that signal to symbol transformation. Once you've got a symbol, which is another word for a word or an icon, you can reason about it. So here's an example of knowledge engineering, which incidentally is a very mature subset of artificial intelligence. Just look it up on the internet. This is a semantic network. It describes the Cadia Ridgeway deposit. It doesn't have all the information about it, but it has a lot of the information, the most important information about alteration minerals and zones, and which zones they're in, and the relationship between the zone. Is it inside the ore envelope or outside it? A mineral deposit model semantic network looks exactly the same. It's just that it deals with probabilities rather than binary facts like true or false. So then, knowledge engineering is the study of the structure and logical behavior of knowledge when expressed on a computer in order to achieve a particular goal. So here's an example of a goal that we want to achieve. Where in Sonora, in northern Mexico, should we be looking for the next porphyry? And this is an extract from real work that we did for a big multinational company targeting porphyries. And what it shows in the hotter colors are cells. These are each 2 by 2 kilometer cells in Sonora. And the red ones are the most prospective, best ones to go and look at on an evidence-based basis. And the ones with no color in them are probably not worth going to. We'll talk about that more in a moment. In order to work like this, artificial intelligence uses frameworks called ontologies within which to store knowledge. Ontologies incorporate taxonomies of all the words we need to use to express knowledge. So for example, the periodic table is a taxonomy. And as geochemists, we know that potassium is an alkali metal. The computer doesn't know that unless you embed the taxonomy in it. And then when it's reasoning, it can recognize when there's the potassium is an alkalic metal. Some other very important examples are the taxonomies of the entire mineral suite, 6,000 of them that we know of today that are named. There are a whole lot more unnamed ones. Sorry, it's going to go forwards. We need to know that arsenopyrite is a sulfide, or that pyrite is a sulfide. We need to know that granite is an acid igneous rock, because if the polygon on your map said acid igneous rock, and the model that you're searching through hundreds of maps for says it needs to be in a granite, you need to know that a granite's an acid igneous rock, because maybe it could occur in that polygon. It may be the other way around. The polygon may be marked as granite, and you're looking for acid igneous rocks. Ontology frameworks also store knowledge about the relationships between words. For example, that alteration is described with minerals and element words. And there's a lot more here. I'm just giving some examples. Tectonic settings in BC terrains, geological time, they're all taxonomic. So here's an example in a mature piece of software which we use called an ontology editor that lets the ontology know that alteration has elements and alteration has minerals. So using ontologies, we describe mineral deposits and deposit models, as I've said before, in semantic networks. Where do we get the models from? Well, many of them are very well documented. We have in our system more than 80 of the USGS deposit models. You can buy the CD with them. They were edited by Cox and Singer a long time ago. Many of them have been updated, but they're still very valuable. The British Columbia Geological Survey under Dave Lefebvre some years ago produced their own systematic documentation of approximately 60 or 70 mineral deposit types that occur in British Columbia. We've got about 30 or 40 of those embedded, ontologically structured in our systems. And as I say, they look just like the semantic network you see there for Ernest Henry. So at the same time, we're able to generate descriptions of locations in 3D space using semantic networks from our GIS databases. So in fact, when sitting in our view of Sonora is a few 100,000 semantic networks that look like this, each one describing a 1 kilometer square part of Sonora, or 2 kilometers, depending on which part of the world we're working in and what the resolution of the data is. We can change the size of that grid. One of the important things we have to do, and there's no way around this for anyone in the world, is to align the vocabularies of the incoming information to the vocabularies we've used to express our knowledge. And that's definitely a bottleneck, but if you address that bottleneck, even better still, if you start using terminology from today going forwards, you're going to be better than your competitor. And you know, with the parallelization of computers now, we can scale this to any scale. We can just bring in additional processors and take the Dick Silito's latest porphyry copper model and run it against 300 or 3 million locations that we've characterized in space. So we compare them and we rank them on similarity. The description of the thing you're looking for, and then the 3 million cells in space, or voxels in 3D space. And we rank them on similarity. And the ones with the highest score are the places where your targets are. Interestingly, they're absolutely auditable because it's a closed system. We've got words coming in and words coming out and parameters that are matched or mismatched. We manage negation explicitly, so that if one alteration assemblage is said to have illite and pyrite and not chlorite, we put in not chlorite. And if another assemblage has got chlorite in it, when those two will be automatically matched, and they'll contribute a negative weighting. And you can see then how important the taxonomy is, because the system needs to know what kind of mineral chloride is. So here's a diagram of how it works really. The knowledge is coming in about mineral deposits from one side, and it's going out of the GIS into semantic networks, into the comparison engine, and back out as scores. So the scores here are kind of overlaid on the grid, but you can see underneath that is a whole lot of points of geochemical information, mineral occurrence information, interpreted geophysics, and so on. On our website or on handouts in our booths, either here where we're showing our outputs in augmented reality, or in booth 500 at the end of lane 500, we have this diagram which better illustrates the closed nature of the system. If we've come up with a wrong recommendation, then we've either got a mistake in our taxonomy, or something wrong with the model, or there's something wrong with the input data. It's a very powerful position to be in, to have a closed system like that. Unfortunately, machine learning doesn't give us that facility. So once we've got our targets, we're able to deliver them in 2D if they're 2D data sets input, in 3D if they leapfrog, and in 3D augmented reality if interpretation of the data calls for that. We don't want you to think that we're an augmented reality company. We are not. But what is different about us is that our augmented reality person sits right next door to the deposit model or deposit camp modeler. So we round trip these things twice in an afternoon if we have to. And if you want to see examples of it, please visit Jake. He's standing there and he's in that little booth. Having it all under one roof is critical, I think. So final slide, I think our current focus is on exploration, but during the year, because we've been financed and we can take on one or two other people now, we'll be expanding our vision to metallurgy and environmental protection, aided by the knowledge overlap in these fields with the knowledge we're already representing about mineral deposits. And there's a little diagram to show it really. If you want to reason about metallurgy, you're reasoning about minerals. You've got to add a little bit more about the different flocculants and chemistry, chemicals that you use with them. But geometallurgy is about minerals and elements and rocks. And an awful lot of environmental protection is as well. So thank you very much, ladies and gentlemen.